Welcome to another Mathologer video. This one is about sex and marriage theorems. Okay, let's start with sex. Statistical surveys regularly report that on average, heterosexual men have more sexual partners than heterosexual women. Now in the description I've linked to an example, a very large Australian survey which included about 10,000 men and 10,000 women who identified themselves as heterosexual. According to this survey, the men had on average 3.9 sexual partners in the previous 5 years. By comparison, the women indicated an average of only 1.9 partners. Less than half that of the men. Absolutely amazing, right? And for the longest time, the experts reporting on these sorts of statistics, as well as the rest of the planet digesting them, just accepted them as fact. Until one day, one mathematician looked at them in just the right way and noticed something very fishy. Alright, here's a picture of the men and the women. Let's draw connections between those men and women who've had sex. Now to calculate the average of the women, we asked them one by one how many partners they have had. So the first woman had one partner, the second also one, the third 3, then 0, and so on. Now to get the average, we just divide by the number of heterosexual women, right? But before we do this, note that this sum is really equal to the number of yellow connections, right? Okay, now divide and you get the average thereafter. We do exactly the same for the men to get their average. Okay, now have a close look. Obviously, the number of heterosexual women in Australia is about the same as that of heterosexual men. So this means that these two averages should really be almost equal. Now, of course, in hindsight, this conclusion seems completely obvious, but seriously, nobody noticed this for decades. And even now, a lot of the specialists don't seem to be aware of this simple argument. So what's the explanation of the strange statistics? Well, some people say that women are more accurate in the way they count partners, with men overestimating. Surprise, surprise. A related factor is the prevalence of sexual double standards. People can simply be too embarrassed or too macho to tell the truth. Well, whatever. I mean, these huge discrepancies really muddy the true figures, making such reports of limited use. And the message we get is likely to be even less useful, since the media tend to only report these impossible averages, right? Okay, now the first person to notice the fishiness in these numbers and to point out the nice visual argument I just showed you is the late David Gale, who used to teach maths at the University of Berkeley in California. Now, David Gale is probably most famous for a paper that also deals with relationships, and that he co-authored with fellow mathematician and economist Gale-Shapley quite a while back in 1962. That was before I was born. So the paper is entitled College Admissions and the Stability of Marriage. Ooh, riveting. Well, in 2012, Gale-Shapley actually received a Nobel Prize in economics mainly for this paper. David Gale lost out because he had died by then. Now, it's an amazing paper in many respects. It's very pretty maths, there's almost no numbers involved, and the results in it turned out to be incredibly powerful in tackling real-life problems arising in the matching of students with colleges, residents with hospitals, organ donors with patients, and so on. But maybe the most amazing feature is that it is possible to explain everything in this paper, including the proofs, in just a couple of minutes. And actually, I'll do this in a second. In fact, the bulk can be understood by anybody with just a bit of common sense. Well, we'll see. And what's also really amazing is that you can get a Nobel Prize in economics for such ingenious, but at the same time, really quite simple mathematics. On the other hand, what I find really very sad is that in the world of professional mathematicians, great ideas with simple explanations are often discounted as trivial. In this world, the best an author of a paper like this can hope for is maybe an expository award, but never ever one of the top prizes. Anyway, here's my best shot explaining everything in this great little article. So to start with, there are an equal number of men and women who all know each other. The question is whether it's possible to marry them off in pairs in a way that is stable. To explain what stable means, picture a man and a woman who are not married, like these two guys. No connection, right? Not married. If that man and woman both prefer each other to their current partners, they may be tempted to cheat on their partners, and their marriages would therefore be unstable, right? Now, for a matching of all the men and women to be stable, that means that there are no unstable marriages, that there is no such man and woman who like each other better than the people they are married to. Makes sense, right? But how likely is it that such a stable matching will actually exist? Well, the surprising answer is that such a cheat-proof matching always exists. And the proof comes in the form of an algorithm, the so-called Gale-Shapley algorithm. Now, the Gale-Shapley algorithm takes the preferences of the men and the women as input and produces a stable pairing as output. To describe the algorithm, I'll use 4 men and 4 women, but it really works for any number of men and women. So imagine that you're Mr. Plus. First, Mr. Plus, just like everybody else, ranks his possible partners of the opposite sex from 1 to 4. In the case of Mr. Plus, we've got this ranking here. So he likes Miss Infinity best, followed by Miss I, and so on. Okay, now it's the job of the man to propose to the women, and for the women to accept or reject according to their preferences. So in round 1 of the Gale-Shapley algorithm, who do you think Mr. Plus proposes to? Well, obviously, Miss Infinity, his favorite. Very predictably, all the other men also propose to their favorites. Okay, so once all the men have proposed, those among the women who have received proposals will agree to provisionally get engaged to, well, obviously, the proposal they like best, right? So if Mr. Plus is really lucky, Miss Infinity will prefer him to all the other suitors, and he'll be provisionally engaged to her at the end of round 1. However, his luck may not last, because in the next round, all the men who are not engaged propose to the next woman on their list, even if that woman is already engaged. Okay, now let's say Mr. Plus is provisionally engaged to Miss Infinity, right? In this round, she may get a few more proposals, and if she likes one of the proposals better than Mr. Plus, she'll dump Mr. Plus and will get engaged to whoever among the proposals she likes best. And that's really all there is to this algorithm. In every round, every unengaged man proposes to the highest ranked woman who has not rejected him outright or dumped him. And the woman will always end up being engaged to her favorite among the men who have proposed to her so far. You just keep on going until everybody is engaged, at which point the engaged couples all marry and live happily ever after. Well, we'll see. All pretty straightforward, but there are 2 questions. 1, how do we know that all this really ends and does not go on forever? And 2, how can we be sure that the resulting matching is stable? Well, firstly, the algorithm does ensure that no man can propose to the same woman twice. And therefore, no matter how many people we're dealing with, only finitely many proposals can be made, right? And the algorithm must terminate. And how will it terminate? Well, once a woman is engaged, she'll be engaged at the end of every round from then on, right? Engaged, stays engaged, and so on. And since every woman is on every man's list, every one of them will eventually be proposed to and therefore be engaged to a man at the end of some round. And since there are the same number of men and women, everybody will then be engaged at this point, and we actually have a matching at the end of this round. It's that easy. Now, the proof that the resulting matching is stable is also not a big deal. Take Mr. Plus again. Now, all the women he likes better than his wife have rejected him and are married to someone they like better than him. This means these women are not interested in cheating with him. On the other hand, he's not interested in any of the other women because he likes his wife better than all of them. So this means that Mr. Plus and similarly none of the other men will ever cheat. And of course that means that the women also won't cheat because they don't have anybody to cheat with. And so our matching is stable. Really neat, isn't it? But it gets even neater. All of this can also be adapted in a straightforward way to work in closely related real-life scenarios. For example, that of students applying to colleges. Where there are fewer colleges than students, the colleges can accept multiple students, can get married to many partners, and can refuse to even consider certain really bad students. Is that all there is to it? Actually, there is much, much, much more. For example, instead of having the man doing the proposing, let's have the women do the proposing and the man the accepting and rejecting. Obviously, that will also result in a stable matching. It's completely symmetrical setup, but usually the stable matching will be quite different from the first matching, right? Also pretty obvious. In fact, it turns out that the Gale-Shapley algorithm very much favors the people who propose. Now, this is intuitively obvious. Let's say the men are proposing again, okay? Then in every round, they get to propose to the highest ranked possible opposite. So for example, in the first round, all the men get to propose to their number one. Whereas the women only get to choose among the men who choose to propose to them. In fact, the overall outcome is even more extreme than that. Let's say this is the outcome of the Gale-Shapley algorithm with the man proposing. Then it's possible to prove that in any other stable matching, every man would be paired with either his Gale-Shapley wife or someone he prefers less. For example, here Mr. Plus was assigned his number 2 choice. This means that in no other stable matching will he ever end up married to his first choice. And what about Mr. Minus? Well, he'll never end up with his first or second choice in any other stable matching, and so on. So the man can never do better than in the Gale-Shapley matching with them proposing. On the other hand, the women fare in the worst possible way. For example, Miss Infinity only gets her number 3 choice, and it cannot get any worse for her in any other stable matching. The important message to take away from all this is that if you are in a situation which calls for a stable matching, using the Gale-Shapley algorithm or maybe just in general, you want to be in the group that does the proposing. And I was actually very pleasantly surprised to find that in all the situations I looked at, where one group consists of institutions like universities and the other consists of real people, things have been arranged for the people to do the proposing. Now, earlier I claimed that I can explain the bulk of the Gale-Shapley paper in a way that basically anybody can understand. Now, how am I doing so far? The only thing missing at this point is really to present an argument that amounts to a proof that the Gale-Shapley algorithm is optimal for the proposing party. I'll do that at the end for those of you who can take a bit more maths, all right? Okay, now since Gale and Shapley wrote their paper, this circle of ideas has been explored in hundreds of other articles and books by mathematicians, computer scientists, and economists. Now I'd just like to mention 2 very interesting facts that have surfaced over the years. First, it turns out that it's impossible for people to game the outcomes of the Gale-Shapley algorithms in their favor by using fake lists of preferences, so lists of preferences that are different from their true ones. Now obviously this is very, very important for when you want to apply this in practice. And second, and this was discovered by my mathematical hero John Conway, the different stable matchings corresponding to a given set of men and women actually form an algebraic structure called a distributive lattice. This means, among other things, that the matchings in many ways behave like numbers. And that any 2 stable matchings can be combined, sort of added, in a simple way to give a 3rd stable matching. Really beautiful stuff. Now I just have to mention this other famous example of a really simple mathematical idea resulting in a Nobel Prize. And you probably all guessed it already. It features in the movie A Beautiful Mind about the mathematician John Nash, who received the 1994 Nobel Prize in economics for one of his least deep results in the world of maths. Anyway, this is the end of the light part of this video. For those of you who can take a bit more, let me provide you with the missing proof. Now, as you can see, the proof in the original paper is really very short. But actually, I don't think you have a chance of understanding it unless you are a mathematician. It's one of those proofs by contradiction. So hopefully my version will be a bit more accessible and actually try to avoid this proof by contradiction business. As I said, apart from the stable matchings produced by the Gale-Shapley algorithms, there may be many more other stable matchings. I want to convince you that no man can do better in any of those other matchings than in the Gale-Shapley matching with the man proposing. Okay, now the following argument is quite devious and you really may have to listen to it twice or even 3 times to really understand it. Okay, now forget about any of the specific examples I talked about so far and let's run the Gale-Shapley algorithm on a small set of men and women in slow motion. To show that the man can never do better in any other matching, we have to check for every man that all the women that rank higher than his Gale-Shapley wife are not married to him in any other matching. Now to systematically do this checking, we just have to follow what happens in the Gale-Shapley algorithm. So what we do is simply check every time a woman rejects a man that these two are not married in any other matching, stable matching. Now once the rejecting stops and we have a stable Gale-Shapley matching, we will have cycled through all the different cases that need to be considered. How do we know whether a woman rejecting a man as part of Gale-Shapley is married to this man in another matching? Well, we could just go brute force, list all the possible matching, and every time we want to know, we'll just have a look. Well, are these two guys married there somewhere? Okay, let's say we do this for a while and as expected we have not found any upgraded marriage. Now, just to make things a bit more tangible, let's say that next Miss Infinity will reject Mr. Plus, let's say at the end of round 7. Doesn't really matter. We could just check again in the other matchings whether Miss Infinity is married to Mr. Plus anywhere. But why don't we try and see whether we can find a general argument that makes this looking up business superfluous. Okay, so Miss Infinity is rejecting Mr. Plus in round 7. This means that the algorithm will end up marrying Mr. Plus to someone he likes less than Miss Infinity, say Miss I. Also, at the same time that Miss Infinity rejects Mr. Plus, she's getting engaged to someone she likes better, say Mr. Times. Now, is it possible that Mr. Plus and Miss Infinity are married in a different stable matching? If so, who is Mr. Times married to in that other matching? Can he be married to someone he likes less than Miss Infinity? Well, no, because in that case, both Miss Infinity and he would like each other better than they like their spouses in that other matching, which would make this matching unstable. Since this is not the case, in that other matching, Mr. Times would have to be married to someone he likes even better than Miss Infinity, say Miss Pi. So to summarize, we conclude that if Mr. Plus was married to Miss Infinity in the other matching, then Mr. Times would also necessarily be married to someone he likes better than Miss Infinity in that matching. All right. However, for Mr. Times to be proposing to Miss Infinity in round 7 means that Miss Pi, who he likes better than Miss Infinity, must have rejected him in an earlier round, say in round 5. On the other hand, since Miss Pi rejects Mr. Times in the Gale-Shapley algorithm, by being married to her in the other matching, Mr. Times actually does better than in the Gale-Shapley matching. So to summarize again, if Mr. Plus did better in the other matching, then Mr. Times would also do better in this other matching. However, since Miss Pi rejects him in round 5, we would already have picked up on this upgraded marriage in round 5, which we said we didn't, right? We checked everything up to round 7 and did not come across any of those upgraded marriages. So since the assumption that Mr. Plus upgrades to Miss Infinity somewhere implies something impossible, we conclude that the upgrade itself is impossible. Miss Infinity and Mr. Plus cannot be married in any other stable matching. Now the same argument shows that no matter which round and which man gets rejected by which woman or dumped, these two can never be married in any other stable matching. And this then finishes the proof. Okay. As I said, you may have to watch this part of the video again really slowly to fully get this. Now, please leave a note in the comments if you do, because I really agonized over this for a long time. And it would be good to know how well this explanation worked for you. I was actually trying to avoid proof by contradiction there, which is part of the original write-up. Well, we'll see. If you are interested in a different take on this stable marriage material, Numberphile did 2 videos on this in 2014. They did present a really cute worked example featuring 8 characters from Pride and Prejudice, and overall I did enjoy the videos a lot. So maybe check out those videos too. And that's it for today.